In this example of balancing a redox equation, a redox reaction, we are going to take a different approach from the oxidation number technique. In this case, we're going to utilize what's called the half reaction technique. So let's look at the reaction that's under consideration. We start off in a similar manner as we did with the first technique. After we've got our equation, we go through and we assign oxidation states to all of the species that are found in the reaction. And then we identify what was oxidized and what was reduced. Now in this situation, it was stipulated that this reaction is going to occur in an acidic condition. So this is in aqueous solution, as most of these reactions are, and it's under acidic conditions, so pH less than 7. That's important because the half reaction technique is modified depending on whether we have a neutral, acidic, or basic set of conditions. So now let's separate out the two reactions that are happening, the two half reactions. So on the left side, I have pulled out the oxidation of copper, and on the right side, I've pulled out those species associated with the reduction of the nitrogen. What we're first going to do is go through both of these equations and balance them atomically. Well, obviously, the first half reaction with the copper, it's already balanced atomically. So we move to our second half reaction, our reduction reaction, and let's go ahead and let's take care of the oxygens that we need. So we need 3 on each side, so you can see I've added in 2 water molecules. So in this technique, that's how you add in extra oxygens that you need, by adding water. I can see, though, I'm still not balanced with the hydrogen, so I'll continue with the reduction half reaction and I'll take care of the hydrogens. And since this is an acidic solution, the way I will do that is by adding appropriate number of hydrogen ions. So I had 4 hydrogens on the right side of the equation. So to get the extra 3 I needed, that is why I brought in the 3 hydrogen ions. So acidic conditions is what stipulated how I was going to take care of the oxygens and the hydrogens. Now what I'm going to do is I'm going to go through both of these reactions and balance them electronically. So you'll notice on the left side what I just did is I needed to get both sides to be 0. So with the +2 on the right side, I added in 2 extra electrons. In my reduction equation, I had one side that again was neutral, the right side, but the left side had those 3 hydrogens, 3 positive charges, so I have to add in 3 electrons to balance them out, and now that equation also is 0 on both sides. Now these two half reactions, of course, they're interconnected with each other. We're having an exchange of electrons take place. So my next technique is to go ahead and make equal the number of electrons being given up by the copper and the number of electrons being accepted by the nitrogens. And obviously between 2 and 3, I've got a common multiple of 6. So I will multiply my oxidation equation by 3. Of course, I have to do that for every term, and I will multiply my reduction equation, half reaction, by 2, and now I've got equal number of electrons being either given up or accepted in the 2 half reactions. So at this juncture, I've taken care of the equations, the half reactions, atomically and charge-wise, and now electronically. And so now I'm ready to take those 2 half reactions and I'm going to put them back together. So here are the 2 half reactions as we've dealt with them up to this moment. and I'm simply going to add them. So everything on the left side will become now the left side of my summation, and everything on the right side of both those equations will become the right side of my summation. And you see this. Then what I do is I look at the ability to cancel things out. If something appears on both sides, I can consolidate them or cancel them out. And the obvious species are the 6 electrons on both sides, so those can be crossed out. I don't see anything else that can be crossed out, so what remains is my final equation, balanced redox equation for this reaction involving copper being oxidized and nitrogen being reduced. And here's my final answer.